This is a diamond, a 580 carat diamond. And they grew it inside this machine. Most people think about diamonds for jewelry, but everybody is missing what is most exciting happening right now. We have built giant machines that can recreate the inside of the earth to grow diamonds, and found brand new ways to make them, which is now unlocking the hidden potential of what turns out to be an incredible super material. Diamonds are wild. They are sending diamonds into space, adding them to massive computers, and using them to try to solve one of the biggest technological problems we are about to face. This story is about pushing the limits of material science to benefit all of us. In this video, we are getting rare access inside a lab where they make diamonds, and we are shrinking down inside a computer to show you why diamonds are not what you think. Diamonds. Lab-grown diamonds. They are not real diamonds. We are reaching the limit. We need more computers. The future of diamond is very exciting. Excuse me while I just hold a fistful of diamonds. This is so cool. Look at all these machines. They are making diamonds in every single one of these. If you wanted to see where a natural diamond is made, you would have to drill a hole way deeper than you think. Most other gemstones, emeralds, sapphires, and rubies form here in the crust. But diamonds come from here, inside the mantle. This extremely hot, thick liquid rock is filled with carbon atoms that are squeezed together over millions of years by pressure 50,000 times what it is here on the surface, forcing them closer and closer until they form bonds with 4 of their neighbors and become diamond. This structure is what makes diamond not just the hardest natural material we know about, but 4 times harder than the next hardest material. And it is why we have already been using diamond for decades to cut, drill, grind, and polish, because diamond can cut through basically anything. But wait, that does not look like a diamond. When you think of lab-grown diamonds, you probably think of this. This is a single crystal diamond. It is the kind that gets cut and polished into jewelry.
So that is grown in our chambers, and over several weeks of time that little seed is converted into that big rough, and that might end up being 2 or 3 carats in the gem.
Excuse me while I just hold a fistful of diamonds again. Be very careful. See these little crystals? They are sharp. So one of the things they are telling me is that the edges are very sharp. So I am going to blow these little fragments off of my hand so they do not get embedded in my skin. Now I have got dangerous diamond debris on my hands. Diamond dust, I guess you could call it. So this is what people might be most familiar with if they know about lab-grown diamonds. This next one is a very different thing. What am I holding here? You are holding a piece of polycrystalline diamond. Instead of growing one single crystal, they grow millions of tiny diamond crystals that bond together, each one only about the width of a human hair. But this particular diamond was not made for cutting or polishing. It was made for something very different, a hidden superpower of diamond that most people do not know about. So I have got this razor made of stainless steel, a very sharp razor. If you put a razor on an ice cube, you can cut it, but it takes some pushing and some time. Now take a diamond and do the same thing. Ready? Look at that. That diamond cuts through ice like it is butter. And this has nothing to do with it being super hard. Instead, it has to do with the incredible way that diamond handles heat. The bonds inside a diamond are short and stiff, but the atoms can still vibrate. When one atom jostles its neighbor, and that one jostles the next, the ripple travels through the crystal, moving heat. Heat can travel incredibly quickly through diamond. Exactly how fast is called its thermal conductivity. And if you look at a chart of other popular materials known for great thermal conductivity, diamond is at the very top. Diamond moves heat better than almost any other material on Earth. So that is why this diamond can cut ice like it is butter. It is stealing the heat from my hand so quickly that my hand feels cold. Okay. So diamonds are insanely good at moving heat. Why does that actually matter? It is time to jump into a computer. You know when you are doing something really intense with your computer and it gets very hot? That is a small example of a much bigger problem holding back basically all of our cutting-edge computers today. That is because most of what is around a computer chip is made of silicon. Silicon Valley, the backbone of computing. Silicon is what makes up the on and off switches that run basically all modern computers. Transistors. More transistors means more processing power, and we have been able to make transistors unbelievably small. This is one of the most unbelievable stories in modern technology. If the first iPod represents one size, the first transistor was far smaller than that. And today's transistors are so much smaller still. Picture the smallest known species of ant, about 1 millimeter long. Now picture a tardigrade, one of my favorite animals, which is smaller still. Now picture the smallest human cell, the red blood cell. Keep going even smaller than a bacterium, and you reach roughly the size of the transistor used in the first iPod, about as big as a flu virus. The transistors in the first Nintendo Wii were smaller still. But we still need to go smaller. If you keep shrinking all the way down, you reach about how small today's transistors actually are. This incredible ability to make transistors smaller has allowed engineers to roughly double the number they can fit onto a chip every 2 years. You may have heard of this. It is called Moore's Law. It is why your pocket-sized phone is over 100 million times faster than the computer that landed us on the moon. But we seem to be hitting a wall. If transistors get much smaller, physics tells us we will not be able to control how they switch anymore. So instead of packing more transistors side by side, like cramming more houses into a neighborhood, engineers have started stacking them, like building multi-story apartments instead of single-family homes. But this generates a lot of heat with nowhere for it to go, and that extra heat is a big problem. All of the better futures we dream about, powered by more computing, more people in space, better cars, better medicines, or cleaner energy, all rely on finding a way to overcome this heat problem. And now researchers think diamonds might be able to help.
We want more speed, we want more performance, more functionality. And all of that is putting enormous pressure on the electronics.
That is one of the world's leading researchers in using diamond layers to cool the inside of computers so they can run faster and do more using less power. We are packing things into smaller and smaller spaces, and the more you push them to run faster and harder, the more heat you generate, and that makes things less efficient until the whole system breaks down. All computers need to move heat off the chip as quickly as possible. That is called heat spreading. Then they need somewhere to dump that heat. A heat sink. Inside your computer, when you hear that fan noise, your chip is generating heat, and a layer of copper on top is trying to pull it off the chip, spread it out, and send it through copper pipes into a set of aluminum fins. The fan you hear blows across the large surface area of those fins to finally carry the heat out of the computer. This is a small problem in your laptop, but a much bigger problem in data centers, electric cars, and satellites. So what if we could use an even more thermally conductive material, like diamond? Diamond seems to be the right material. The idea is to grow diamond directly onto chips, like a blanket that helps pull the heat away much faster. Our work showed that if you wrap a chip in diamond like a blanket, you can make the transistors run cooler and therefore far more efficient than they would be otherwise. But you cannot do this with natural diamonds, not just because mining them is so expensive, but because many natural diamonds have trapped impurities from when they formed, which make them worse at moving heat. So the only reason this approach is possible now is that we have become unbelievably good at growing extremely pure diamonds, and how they do it is remarkable. On the way to the diamond lab, I was researching the first time anyone ever grew a diamond, and I found declassified CIA documents about it. The first time anyone ever grew a diamond was in a secret project after World War II. Declassified CIA documents show that the United States needed about 5 million carats of diamonds a year to grind, drill, and cut parts for airplanes, tanks, and armor. So General Electric's research lab set out to make them. They called it Project Superpressure, because they used a giant machine similar to the ones used today that recreates conditions like the inside of the Earth. It works by taking superpure carbon powder, adding a metal flux, and heating it to over 1,000 degrees Celsius to create a molten mixture like the one found in the mantle. But instead of relying on the weight of the planet, this machine uses powerful arms to compress the mixture, creating pressure equivalent to placing a commercial airplane on your fingertip. But all that pressure and heat will not make a diamond unless you also have a tiny diamond seed, which gives the carbon atoms something to grip onto. This speeds up the growing process from millions of years down to less than a week. They called this method high pressure, high temperature. But today, labs often use a newer method instead, and now it is time to grow a diamond myself. It is kind of like baking a cake. The first ingredient, just like in the high pressure, high temperature method, is a diamond seed, which tells the carbon atoms what molecular structure to form. Instead of placing it between giant arms, you place it on a heat-resistant metal puck and put it into a chamber. The first thing the machine does is pump out all the air from the chamber, so only the ingredients needed to make a pure diamond remain. The first ingredient added is hydrogen gas, which helps build the crystal. Then the chamber becomes a large, powerful microwave, about 10 times as powerful as the one in your kitchen. These microwaves give the hydrogen molecules energy, creating a cloud of plasma gas that can break apart molecules. Then you can see the plasma appear, glowing around the puck where the diamonds will grow. The final ingredient needed is carbon, added as methane gas, CH4. When the methane is introduced, the plasma changes color, turning green as the reaction begins. The energy in the plasma breaks the methane apart into carbon and hydrogen, and over time the carbon atoms deposit onto the seed and the crystal grows. This method is called chemical vapor deposition. If the conditions are kept just right for weeks, you get diamonds that can be cut into gems. But to grow the polycrystalline kind, you do not even need a seed at all. And there it is, a newly grown diamond. These are all diamonds, but they started out as nothing more than microwaved methane and hydrogen. These lab-grown diamonds are even more pure than the ones found in the Earth, which makes them better at moving heat. And they can be grown into almost any shape. This process has become so fast and so reliable that experts now say a diamond layer on every chip is not a science fiction idea. It is very real and very possible. In fact, there are already data centers using diamond-cooled servers right now. The world's first diamond-cooled server reportedly used an Nvidia H200 chip. And there are diamond-filled satellites in space, helping shrink their size, since a large portion of a satellite's design goes toward managing electronics and heat. Diamonds in data centers in particular could be a big deal if they let companies get far more computing power with far less hardware. And the early evidence suggests they can. This is a genuine breakthrough, and the data is recent. A test done last week in a data center in San Francisco reportedly doubled the amount of compute coming off a single GPU. To be clear, this is still experimental, a large-scale test. But if it holds up, it implies a future with fewer data centers producing the same amount of computing power. Instead of building 2 regular data centers, you could build one. Today's applications are looking for a 2 degrees Celsius reduction in temperature. Some of this work has shown a reduction of up to 70 degrees Celsius. Beyond more efficient data centers, diamond has other hidden strengths that researchers are only beginning to explore, like its ability to handle extremely high voltages, which could, in theory, lead to very effective diamond-based transistors, or its resistance to radiation, which makes it useful in space and in large-scale experiments here on Earth. and even its compatibility with the human body, which makes diamond promising as a tool for drug delivery. All of this is exciting, but still unproven. To be clear, we do not yet know how much of this will pan out. It is an exciting moment for material science. No one knows exactly what role diamonds will play in the future of computing. We are figuring it out right now, and that is what makes it so exciting. It is a large-scale experiment using a material we have long associated with jewelry for something much bigger, because we figured out how to recreate the conditions inside our own planet, to produce something only nature could make before, using technology that has become good enough to explore new ways it can benefit both people and the planet that made it in the first place. If you believe in optimistic science and technology stories, share this with someone who needs to hear it. Like and subscribe, and thanks for watching.